In Chapter 5, we've been focusing on probability distributions. We learned just some of the basics of a probability distribution, and then we've also learned about a specific type, the binomial distribution. Today we're going to finish up learning about 4 other types of probability distributions. The first one is called the multinomial distribution. It's used when each trial in the experiment has more than 2 outcomes. When we had our binomial experiment, we can only have 2 outcomes. A multinomial distribution satisfies the following requirements. There must be a fixed number of trials. Each trial has a specific, but not necessarily the same number of outcomes. The trials are independent, and the probability of a particular outcome remains the same. The formula for the multinomial distribution, you see a lot of variables we're already familiar with. Capital P of x is our probability of whatever the event happens to be. Our lowercase n is still the number of trials. The capital X's are representing each outcome, and the lowercase p's are representing the probability of success for each particular outcome. So in example 1, we have a card drawn randomly from an ordinary deck of cards and replaced. Remember, our trials have to be independent of one another. So if I don't replace the card, my trials are no longer independent. This is repeated 5 times. What's the probability of drawing 1 spade, 1 heart, 1 diamond, and 2 clubs? So I'm going to go ahead and start with our probability notation. So probability of, we want 1 spade, 1 heart, 1 diamond, 2 clubs. In our numerator, we have an n factorial. That's how many trials we have. And it says we're going to draw the card 5 times. So our numerator starts with a 5 factorial. The denominator represents how many we want of each different outcome. So I want 1 spade, I want 1 heart, 1 diamond, and I want 2 clubs. So how many do I want of each particular outcome? And now I have to multiply by those corresponding probabilities. So if I have the probability of drawing a spade, there's 13 spades in the deck out of 52 cards. How many of those do I want? I just want 1. How many hearts do I have in the deck? Still 13 out of 52. I want 1 heart. 13 out of 52 for our diamond. And I just want 1 diamond. 13 out of 52 for clubs, but I want 2 of those. We do a little computation, and we end up with 15 out of 256, or approximately 0.059. If you haven't had a chance yet to try example 2, take a pause here and try example 2 before listening to my explanation. In example 2, we have 10 marbles in a bowl. 2 are red, 3 green, and 5 blue. 4 marbles are randomly selected with replacement. What is the probability of selecting 2 green and 2 blue? So we want the probability of 2 green and 2 blue. My numerator is the total number of trials I want. We're going to draw 4 marbles. Then the denominator represents how many of each outcome I want. I don't want any of the reds. I want 2 greens, and I want 2 blues. Corresponding probabilities. Probability I draw a red is 2 out of 10, or you could put a 5th, or I know the decimals are usually easier to enter into the calculator. Probability I draw a green is 3 out of 10, and I want 2 of those. Probability I draw of blue is 1/2, and I want 2 of those. We do a little computation. The fraction would be 27/200, decimal 1.35. So again, that's the multinomial distribution. You have more than 2 outcomes, but remember those trials are still independent of each other. The next distribution we're going to look at today is called the Poisson distribution. It's when your n is large and your probability of success is small. The independent variable occurs over a period of time, or a density of items is distributed over a given area or volume. The Poisson distribution satisfies the following requirements. The random variable x is the number of occurrences of an event over some interval, so whether it's length, area, volume, period of time. The occurrences occur randomly. The occurrences are independent of one another. And the average number of occurrences over an interval has to be known. The formula for the Poisson distribution. We have a couple new variables for us. We have lambda. Lambda is the mean number of occurrences per unit, so whether you're talking time, volume, area, whatever it happens to be. And then we have our E, which is approximately 2.7183. For the Poisson distribution, aside from just entering the formula into your calculator, substituting in all the correct values for your variables, there is a calculator shortcut you can find on page 300. It's super similar to the binomial distribution. And then there's also table C in appendix A, which is on page 780. So just like with the binomial distribution, you have a couple different options if you don't want to just have to plug and chug in the formula. So let's apply this distribution. Official records in a particular city show that the average number of school closings in a school year due to snowstorms is 4. What is the probability that there will be 6 school closings this year because of snowstorms? So we're looking at it for a particular time frame. Probability of this is my capital X, so how many successes I want. And then this is your lambda, which is representing the average. So we have E to the negative lambda times lambda to the capital X divided by capital X factorial. So roughly if you want to try some of the calculator stuff or check out the table, you are more than welcome to. I'd be more than happy to help you out with any of that if you're unsure of any of the steps. If you haven't had a chance yet to try out example 4, please do so before you listen to my explanation. From past experience, a baseball club owner knows that about 6 games on average will have to be postponed during the season because of rain. Find the probability that this season will have 3 games postponed, at most 3 games postponed, and at least 3 games postponed. So if I just want 3 games postponed, that's like wanting our 6 snow days. I want 3 successes. My average has been found to be 6. So whether you want to use the formula, whether you use the table, or whether you use the calculator, That's what we should come up with. Now, if we get into the at most 3 games, at most 3 games means 3 is the most that I want. So that means we're talking about our x value being 0, 1, 2, or 3. So that means I need to find the probability of 0 games being postponed, plus the probability of 1 being postponed, plus the probability of 2 being postponed, plus the probability that 3 are postponed. Now again, if you want to, you could use the Poisson CDF in your calculator. You could also use the table to very quickly get these individual values. Now for the at least 3 games, that means I want my x to be, well, they don't give us a total number of games, so I'm kind of stuck. It's just the probability that this season, how many games are going to be postponed. So for at least 3, what I'm going to have to do, so I don't know where this stops. I don't know how many games total there are. So I have to do 1 minus the probability of 0 games plus the probability of 1 game plus the probability of 2 games. So anything less than 3, I'm going to do 1 minus those probabilities added together. Now if we look up above, we already have those 3 separate probabilities. We add those 3 together. And here's what we come up with. Now if you choose to use the calculator, it might provide a little bit more exact answer, but don't worry about that. If you're a little off, that's okay. It's going to depend if you use the table. The table rounds the values. The calculator will give you the more exact answer. Our third distribution is called the hypergeometric distribution. It's used when there are 2 outcomes and sampling is done without replacement. Satisfies the requirements of there being a fixed number of trials. There's 2 outcomes, and they can be classified as success or failure. The sample is selected without replacement. So here's where we're varying big time from our binomial distribution. Now we're without replacement. The formula for the hypergeometric distribution, we see some combinations in there. If you add your A and your B together, that should be the total population that you have. So if we take a look at the hypergeometric distribution, we have a faculty-student committee is to be selected at random from 3 students and 6 faculty members. The committee is to consist of 5 people. Find the probability that the committee will contain exactly 2 students. Now I know this question doesn't specifically say without replacement, but I can't select one person to be both members of the committee that we're looking for, or all 5 members, I should say. So we want the probability that we're going to get 2 students. So once they're already selected, I can't select them again. So this is done without replacement, but it's not going to specifically say that. So I have 3 students that I want to choose 2 from. And then I have 6 faculty members that I need to choose the rest of the committee from. So if I want 5 people, I need to choose 3 of them. Then I have 9 total people to select from. I want 5 for my committee. Now I know this looks very familiar to you This is simply looking at when we found the probabilities using our combination rule. So very similar. So in essence, you guys have already learned and worked with the hypergeometric distribution without actually knowing it. If you haven't had a chance to try example 6 yet, please go ahead and try that out before I go through it. Of a shipment of 100 radios, it is known that 10 are defective. If 8 radios are randomly selected without replacement, find the probability that 6 radios are defective. So probability of 6 defective. There are 10 total defectives. I want to choose 6 of them. Then there's 90 that are not defective. I want to choose 2 of those for a total of 8. There's 100 total radios. I want to choose 8 of them. So roughly, and I apologize guys, I just realized I didn't give you the answer to the last example. Should come out to be 10/21. Sorry, example 5, if you flip back to that, should be 10/21. Our last type of probability distribution is known as the geometric distribution, used when the experiment has 2 outcomes and is repeated until a successful outcome is obtained. It satisfies the following requirements. Each trial has 2 outcomes that can either be success or failure. The outcomes are independent of each other. The probability of success is the same for each trial. And the experiment continues until a success is obtained. I know you're reading through it, Miss Galley, that sounds an awful lot like the binomial one we already did. The difference is, though, the experiment's going to keep going until you get success. Let's take a look at the formula, then we'll apply this. The formula, we still have our lowercase n and our lowercase p. N is still the number of trials, p is still our probability of success. So for example, a die is rolled. Find the probability of getting a 4 on the 5th roll. So I want to keep this experiment going until I get a 4 on the 5th roll. So probability 4 on the 5th roll. Probability that I get a 4 is 1/6. 1 minus my probability of success. My total number of trials, in this case, I want this success to happen on the 5th roll. We do an n minus 1. This approximately comes out to be 0.080. If you haven't had a chance to try number 8 yet, please do so before I do. Number 8, 2006, 86% of households had cable TV. If 3 houses are selected at random, find the probability that the 3rd house selected is the first one selected with cable. So I'm not looking at all 3 houses being selected with cable. We've done those types of questions before. Now I'm looking at very specifically that the 3rd house is the first one selected with cable. So probability 3rd house. Probability that they have cable, probability of success is 86%. 1 minus our 86%. The number trial I want the success on is 3. We do an n minus 1. So we get, plug and chug in the calculator. Or if you want to round, approximately 0.017. Make sure that you have read all of chapters 4 and 5 up to this point. Make sure you've outlined 5.4. your assignment, I would recommend at least doing the odds. When you can use a table, like with the Poisson distribution, or use calculator with the Poisson distribution, try it out. You may use any tables on the test, and you're also more than welcome to use your calculator on the test as well.